very quickly, so I need my notes because I don't really know him. So, Florian Gallien just finished his PhD in materials at the European Space Agency. And yes, I say PhD in materials, apparently it is considered also as science, as I've heard. So he's going to talk tonight about how to be shot at 20,000 kilometers per hour and survive. So tighten up your seatbelt for liftoff with Florian.
Okay, hi guys, girls, gentlemen, ladies. Is it okay, the microphone? Yeah. It's my pleasure to welcome you at your, I think it's your first and only masterclass in how to be shot at 27,000 kilometers per hour and survive. So first of all, I think you have like a burning question in your brain. Why the hell of the 27,000 kilometers per hour? Why not 20, 30? This is really simple, you all know it, but I'm gonna make a quick recap. So this is gonna be explained by the canon of Newton. So basically it explains the principle of going into orbit. So let's imagine you're on Earth, on the top of a really huge mountain, let's say Everest. You remove the atmosphere, so no air drag, no friction, nothing. You have the cannon aligned horizontally and you shot. So the ball is going at some distance. After you shot it faster, it's going to be further and again further and further until one point where the ball is just not touching the Earth anymore, it's just going into orbit. So basically going into orbit is just a matter of energy and velocity. So the second thing is the velocity needs to go into orbit is not the same depending on the altitude. Basically, the higher you go, the slower you need to be to orbit. So this you can see it if you take a look at this is the solar system, a bit better than this one. So if you take a look at Mercury and Saturn, you can see like Mercury is spinning faster than Saturn. So that's really show the dependency on altitude of the velocity. And now, why 27,000 kilometers per hour? This is just because I'm pretty sure you all know about International Space Station, this really nice Lego toys, which the construction starts like in 1998, which is the same as Galaxy Chloe. And if you take the altitude of the ISS, which is roughly 400 kilometers per hour. Is it okay now?
Yeah.
Yes. If you take the altitude of 400 kilometers per hour, you get the velocity of 27,000 kilometers per hour. Okay. So, another fun fact is 400 kilometers per hour seems high, but it's really low for an orbit for a spacecraft. You still have. Is it okay? So, it seems high, but it's still low. So you still have some residual atmosphere, so you still have some drag. So if you let the ISS just spinning around the Earth, it's going down and down and down every day. So you need to push it up, like I think it's every 6 months. And this is done by a Progress, which is a Russian space cargo. I think you got it. So now let's dive into the lesson one. Lesson one, when you want to survive, it's know your opponents. Your opponents at 27,000 kilometers per hour is going to be debris. Debris can be either as huge as this rocket body. By the way, does someone knows which one is it? No. Nobody wants to try. Okay, this is the third stage of a Saturn V rocket, which brings the man on the moon. And so it can be as big as this, but as slow as this. Just take a look there. You see the small pieces? This is coming from the stage separation of a rocket. So the debris can range from some millimeter size to like rocket bodies. So this is your opponents for today. So now you know that. Let's dive into the dispersion of the debris. So this is a movie. Yeah, it starts. So this schematically represents the population of everything which is up there from 1957, which was the launch of the Sputnik 1, until 2015. So you can see it's kind of a bit crowded there. To be honest with the movie, the size of the dots is really exaggerated in size. So it's not like the Wall-E movie. It's not yet like this, but if you continue, it might be like this. So this is going a bit further into the details. This graph represents the total of objects you have up there. Use satellites, ongoing satellites, rocket bodies, fragmentation, debris, and everything. Like also the space car of Elon Musk. So you have the debris from 1957 until 2012. And you can see it's like linearly increasing until this, where you have two bumps. The first bumps was like the best idea of the Chinese, which was to try if they can shoot one of their satellites up there. So they unfortunately succeed. And this is the estimated orbits you get from the debris. So from one dot, which were the satellites, you get all this around the Earth. The second one, the second bump, is what we thought before it would be impossible. It's a collision between two satellites. So you have an American one, Iridium, which were in use, and a Russian, Soviet one, nobody knows. And you create these like clouds of debris. And fancy doing the presentation today, because I'm the guy who's doing the things much earlier. India also states that they succeeded in the last month to shoot one of the satellites. So you should expect another bumps into the debris. So that states the lesson one, and you know your opponents. So basically it's going from sub-millimeter size debris to huge rocket bodies. Now lesson two, you might say, well, okay, small millimeter size rocket body, but doesn't matter. The thing is, keep in mind the 27,000 kilometers per hour. This is the effect of an impact of small size debris with such a velocity. There you have like impact on a dense aluminum block of a ball this size. So you have the effects at 7 kilometers per second, which is the velocity. I saw you. This is like an impact on the ISS, solar panels of the ISS. So you need some guys to fix it, like high qualified technicians. We have one there also, I think. This is also the MMOD on another part of the ISS, which like all the red circles shows the impact on the parts. And this is small white dots. It's an impact on the window of the cupola. So this is lesson two. You have to keep in mind, like even the smallest debris is really a threat for you. So now, before I'm jumping to lesson three, I'm going to make you work a bit and think a bit. So you know you have small debris, big debris, really huge impact on your spacecraft, and you need to choose for the strategy. Basically, you can think about two strategies. Just avoid it, or just, face it like a man and block it, okay? So I need to know now, in the audience, who think like to avoid the debris is the best strategy. Team Matrix, can you raise your hands, please? Okay. So who, like Team Captain America, who thinks like blocking is the better? It's like kind of 50-50, that's nice one. Okay, so that was the easiest question, so you all right. In fact, it depends on the size of the debris. Because as you know, size matters. And this is another question for you. So you know, the strategy, you can use both, but it depends on the strategy. So I'm going to ask you the question now. So you have like 6 order of magnitude of sizes. You have same grain, like 5 cents pennies, golf ball, CD. By the way, CD for the youngest one is like the USB key of the 90s. Okay. A luggage and a small car. So I'm going to ask you first the question, what's the maximal size you can shield according to you? Someone want to try? Yeah?
I think the golf ball will be too much to shield. No, maybe.
So the question is, what's the maximal size you yeah. So golf ball for you, it's too much.
No,
so,
well, maybe we can shield at least, but not.
The speed is 27,000 kilometers per hour. Yeah. Whoa. Okay, so golf ball we got 5 cents. Smallest 5 cents, right? Okay. And now the second question is, what's the minimum size to be tracked from the ground to perform an avoidance maneuver? CD? Yeah. Another guess? Just one guess. The other one's like, I prefer my beer. Okay, the answer are pretty much right. For the avoidance maneuver, it's like all the debris bigger than a CD or a fist, basically. So you can see from ground, and so you can say to the spacecraft or to the ISS to perform an avoidance maneuver. Everything smaller than basically the 5 cents pennies, you can shield it. So I know now you're gonna ask what's happened between the two. So that's gonna be the third strategy. You just pray. Basically, you cannot shield it and you cannot see it. So it's never. I mean, I don't know that it ever happened before, but I think there is in a Gravity movie when a bird gets shot. You have like an astronaut with the face with the hole in. Yeah, no, don't remember. Okay, just take a look at Gravity tonight and you will remember what I said. So that's the lesson 3. You need to choose the right move. You need to run or fight, depending on the size of the debris. Okay? So now let's think just small debris. Okay? We want to face it, like a man or woman. So now you need to think about the strategy to shield it. Is it like using a heavy bulk metal plate to shield it? Is it like with laser? You just take a look at the debris and just shoot at it? Is it like, I don't care about the debris, I just do nothing? Is it like magnetic field? Is it metal plate? Any guess? Metal. So this one? The big one? So this one? Okay. Another guess?
Big one.
The big one? Yeah, the big one. That's it? Well, these two, for sure that was the trick. Didn't fail into it, that's nice. This one works, but you have to remember that in space you really want to have the lightest things possible. So for sure, if you put like a 1 meter thick steel plate, it's going to block everything. But it's going to be super heavy. And if you want to speak about efficiency in terms of weight, in fact, the solution is a combination of the thin metal plate and I don't care. Okay? So, lesson 4 is like, just check what the experts do. I mean, you just need to survive, you don't need to reinvent the wheel, okay? So that's the strategy they use right now on ISS. So basically you have like thin metal plates or layers with a standoff of nothing. Why is that? So you can see this is called Whipple, which is a specific type of shielding. And so this is basically the effect of the bumper. The bumper, which is the first layer, is, I mean, the objective is not to block the debris, but it's really to spread the load on a wider surface. So basically, you came from like a really localized projectile to a really large debris clouds. It's like you're going to a trek in winter and you want to walk on the snow, and you have to choose between normal shoes and high heels. I'm pretty sure you all choose the normal shoes, right? And this is why, because you're going to spread your load on a wider surface, so basically the stress is going to be lower. This is the reason why it's so efficient, this design. It's because it's going to spread the localized impact of the projectile to a wider surface. And you have here some example of real, in life, testing of these kind of shields. So jumping into the example, if you take a look at the ISS, and more precisely at the front. So this is the front of the ISS, this is the back, and basically it's moving like this. This is the front. In the front you have like the Japanese experimental module, which is called Kibo. You have the European module, which is Columbus, and you have the US lab. I think it's Destiny, but I'm not sure. And all 3 of them used a special kind of Whipple shield, which is the stuffed one, which is the simple one. And right at the middle, you have a really strong fabric, which is the Kevlar. Basically, it's the fabric which is used also for the bulletproof jacket. So if you, I know someone might be scared because there is graph and maybe equations, and but keep it easy, it's going to be simple. So this is the graph which represents basically the performances of the shields. It plots the critical projectile diameter at a certain velocity, at which, I mean, smaller than this diameter, your shield is going to protect you. Above this side is going to be penetrated by the projectile. So basically these curves are the limits which, I mean, stand for the protection performances. Everything which is below, you're safe. Everything you are above, you can be in trouble. The funny fact is, you can see it's not like, you should expect the faster is going the projectile, the lower is the critical diameter. But you can see you have a switch in this train. It's going down for the beginning, up and down again. In fact, this is explained also by the fact that if you are low speed, I would say low speed, but it's less than 3 kilometers per second. It's not so low. You just fragment your debris from I would say, a large pieces to small pieces, but everything stays solid. I mean, in the solid phase. If you increase the speed, you start to create liquid. For example, if it's an aluminum projectile, you're going to start to create liquid aluminum, gaseous aluminum. How do you think about it? I mean, aluminum gas. I mean, that's crazy for material scientists. So, in this portion, you basically transform the solid into liquid and gas. That's why you gain, I mean, performance into the shield. And at this point, there is no more solid to be transformed. So you just get up with liquid and gas. So by the way, when you create like solid aluminum directly from gaseous aluminum, that's called sublimate. All right, so that's the end of the lesson 4. Now lesson 5. Once you know everything, you know the debris, you know the strategy, you know how to do it, you need to practice. Okay, you have 2 solutions. Or you go up there, you stand in space, waiting to be hit and see if it performs well. Or the less expensive one is to try it on ground. How is it done? Basically, it's more like compressed air gun than the one you use where you were kids, like to shot plastic balls. But I was the only one doing this? It's the same thing, but you shot like aluminum pellet at 7 to 10 kilometers per second. And the same. It can be fired or by compressed air or by explosive charge. Basically, it's the huge difference between Europe and USA. You know, Europe, we prefer to be safe, we use compressed air. USA doesn't really care, make explosive stuff. So basically, you compress, your projectile is just sitting here in the plastic case. You compress the air in front, which push the projectile. After, you have a specific chamber with, it's not vacuum, it's just like a really, really tiny atmosphere. Just enough to separate the plastic case from the projectile. You can see it there. And after you have the projectile is going through and hits your shields. So that's real movie from the test in Fraunhofer Institute, which is in Germany. And you can see really I would say the transformation from the debris to the debris clouds. And you can see it's really acting like a wave. It's more like liquid and gas. So this is the pictures of this kind of gun. I had the opportunity to play with it. That was nice. You cannot do this for physicists. And this is like, it's between 7 and 10 meters long. And you can have like 3 or more stages. I mean, not just one like this, but you can have 1, 2, or 3 stages. So basically, the lesson 5 is just practice. Okay? If you want to survive at such an impact. So now, the recap. I need you to see if you were awake. Not too much. So lesson 1 was... okay. Did you copy, Houston? Lesson 1 was know your opponents, yes. So the debris size. So lesson 2 was keep in mind the risks. So remember what might happen if you do nothing. Lesson 3 was yes. Lesson 4 was kind of almost. But master the solution. Check what the experts do and master the solution. And lesson 5? Yes, practice. So that's the end of the masterclass for me. Just before the question, do not forget to fuel the rocket because the journey is not continuing after it. And the amount of fuel you put in is gonna make the next destination or Mars or Earth. So any questions? I think you can.
So do we have any questions?